presentation by Jiwon Seo. He's a PhD student of Stanford University. And today's his presentation title is slightly changed from the program. The title is SociaLite Python Integrated Query Language for Big Data Analysis. Please.
Okay. So a little bit about this background. SociaLite was a research project at Stanford University, and now we are trying to make it a really usable open source project. A little bit about this motivation. So why do we need another big data analysis framework? Because there are plenty of big data analysis framework on Hadoop. That is because the existing platforms frameworks has these problems. For example, most existing data analysis platforms are too difficult to use, even for very experienced programmers. That is because they provide very low-level primitives. Hadoop MapReduce programming model, for example, can be useful for certain tasks such as counting word or processing very simple logs, but it's not good for implementing, for example, k-means clustering algorithm. It's just that their API is too low level. Second, existing platforms are very inefficient because they are not designed to fully utilize network bandwidth. And in most cases, for distributed data analysis programs, they should be network bandwidth bound, which is not the case with the existing platforms. On top of that, with the existing platforms, if you want to do slightly different tasks, you need to learn very different frameworks. If you want to do large-scale graph analysis, you need to learn framework A. And if you want to do big data mining, you need to learn framework B, which is very different from framework A. And for relational queries, you need yet another framework. And this requires too much effort from programmers, and that's why we come up with SociaLite. SociaLite is a high-level query language that is very easy and efficient. We provide high-level primitives, and the queries are compiled down to very efficient parallel and distributed code. The compiled code is very fast as 1,000 times faster than equivalent Hadoop data analysis programs. If you run it on an InfiniBand network, if you run it on a 10 gigabit Ethernet, it's somewhere between 100 times to 1,000 times faster. We are Hadoop compatible, meaning that we can read and write from Hadoop distributed file system. And we have Python integration, mostly Jython, and potentially it's possible to integrate it with CPython as well. And this single query language is good for large-scale graph analysis, data mining, and relational queries. So when I say Python integration, I mean this kind of integration where you can intermingle Python code and SociaLite query in RAD. And you can also access Python variable from SociaLite queries. Okay. So with that, I'd like to give you the outline of this talk. First, I'm going to give you the programming concepts in SociaLite, distributed tables, rules, and its Python integration. And then I'm going to describe some of the analysis algorithms in SociaLite, graph algorithms and data mining algorithms. And I will give you some evaluation numbers. And if I have time, I will give you a demo. And if I do not have time, I will still give you a demo during the break. So if you want to watch the demo, please stay. So distributed in-memory tables are primary data structure in SociaLite to store user data. So it's column-oriented storage, meaning that the element in the same column are contiguously stored in memory. So you can use this kind of statement to declare or create SociaLite table. First, you write the name of the table, followed by column declarations. The type of the column can be primitive types, such as int, long, float, double, or it can also be object types, such as string, or any user-defined types. So let me give you some specific example. We have 4 table declarations. The first one here creates a table named foo, having 2 int columns. An example of this table would be something like this, having 4 tuples. The second one declares table foo, but in this case, the second column is nested with this parenthesis. An example of this foo table would be something like this, where the Second column is nested. So notice that these two tables represent the exactly same set of tuples. And this guy saves some amount of memory. And this comes in handy when you store graphs. So you can store edges, source node, and target node. The third one here with the angular bracket declares a distributed table where the table is horizontally partitioned with respect to the value of this partitioning column. So if you have two machines, the bar table would be partitioned like this and stored across the machines. The last one here has this 0.10, which is called range operator. That indicates that the value of this column is between 0 and 10. In that case, we apply range-based partitioning, where for the tuples whose first column value is between 0 and 5 are stored in machine 1 if you have two machines, and tuples whose first column value is 6 to 10 are stored in machine 2. So compare it with the previous case where we applied hash-based partitioning. Okay. We also make it possible for you to control the structure of the table. For example, you can add indexing to a column, or you can sort by a specific column, or you can declare that this is a multi-set, not a simple set. So once you declare a table like that, you can use SociaLite rules to process the data and apply, for example, relational operations. Here, we have an example of SociaLite rule. What is on the left-hand side of colon dash is called rule body, and what is on the right-hand side is, what is on the left-hand side is rule head, and what is on the right-hand side is rule body. So here, roughly, we are joining these two tables in the rule body and store the result in full table. So let me give you an example. So here we have bar table and quarks table with 5 tuples, and full table is empty. So as we evaluate this rule, we go over the tuples in bar table, and for each tuple in bar table, we go over the tuples in quarks table, trying to find the matching tuples where the second column of the bar table matches with the first column of quarks table. That is because we use the same variable name here, so we want them to be equivalent. So we have two matching tuples for the first tuple here, and we have another matching tuple. So we stored the results into the full table, but only the first column and last column, because we are only storing A and C. So let's have another look at this example. So these are distributed tables. So if you have two machines, the tables are partitioned into two and stored across like this. For this tuple in bar table here, we have matching tuples on machine 2. So for this join operation, the SociaLite runtime automatically transfers this tuple to machine 2 and do the join operation, and transfer the join result back to wherever it should be stored and store it into the right partition. So of course we do not transfer a single tuple at a time. We accumulate some number of tuples in a temporary table and transfer that in a single message. So we pipeline this communication and computation such that we fully utilize CPU and network bandwidth. If you use 10 gigabit Ethernet, which gives you about 1 gigabit per second bandwidth, we fully utilize its entire bandwidth. If you use InfiniBand, which gives you about 5 gigabyte per second, we can utilize about a little less than half of it, which is about 2 gigabyte per second, which is far better than any of existing big data analysis platform. So while we do this distributed computation all automatically behind the scene, we make it possible for users to control this communication pattern a little bit by the ordering of the table in the rule body. So if you have bar table first, we transfer the tuples in the bar table to where the matching tuples are stored, as in the previous case. But if you reverse it and have quarks table first and then bar table, we transfer the tuples in quarks table to where the matching tuples in bar table are stored. So going back, in the previous case, when we do the distributed join operation, we know the value of B already, which is from bar table. So this is in the partitioning column. So we know exactly where the matching tuples are potentially located. So we know where to send it to. But in this case, we do not know the value of A until we actually do the join operation. So we need to broadcast the tuples in quarks table to the rest of the machines. Depending on the relative size of the tables, this may or may not be better than a previous case. And the relative size of the tables are something that programmers are typically aware of. So we let the programmers to determine the communication pattern by the ordering of the tables. But of course, it's potentially possible in the future for the SociaLite runtime system to automatically optimize this and minimize the communication volume. Okay. So let me use the same rule here to describe how we make use of multiple cores. So given two machines, we partition the tables into two pieces. But for each partition on each machine, is further divided into sub-partitions. And given a SociaLite rule like this, we create multiple evaluation tasks, as many as the number of sub-partitions in the first table in the rule body. So in this case, we create 8 rule evaluation tasks in total, like this, 4 on each machine. And these tasks are dynamically scheduled to be executed by multiple cores in parallel. And each of these tasks operates on single sub-partition at a time. For example, this guy here joins the first sub-partition of bar table on machine 1 with Cox table. Okay? And we automatically add synchronization code as necessary, so you don't need to worry about the synchronization at all. So aggregation is very important in data analysis. So we support it in SociaLite. You can use aggregation by having this aggregate function in the rule body. And the semantic is that for the tuples in full table, we group the tuples by the values of the column that are before the aggregate function. In this case, we group the tuples by the value A, and then apply this aggregate function to the tuples in the same group. So we have built-in aggregate functions for common aggregate operations, min, max, sum, average, argmin. We also make it possible for users to define their own aggregate functions in Java or Python. So one thing that makes SociaLite different from other kind of query language is we support recursion, which is important for graph algorithms, which often incurs recursive traversal from node A to node B, for example, BFS. Recursive rules are indicated by having the same table name in the rule head and rule body. And the semantic is that we evaluate this rule repeatedly until there is no changes to head table. So we evaluate this once and add tuples to full table. And with that added tuple, we evaluate this again. And we repeat this until we add no tuples to the full table. So this recursive rule with aggregate function allows us to very efficiently implement some core graph algorithms. For example, shortest path algorithm implemented here. So we assume that the graph is stored in this edge table, source node, target node, edge length. And after we evaluate this, the path table stores the result. For each node, it stores the shortest distance from source node. So here we are computing basically shortest distance from a single source node to the rest of the node. So we have two rule bodies, which simply means that we apply this aggregate function to all the tuples from both rule bodies. And the first rule body is the base case of the recursion, where you're setting the distance to the source node itself is 0. And we add that to the path table, which triggers this recursion. And for that source node, we go over the neighbor node of that source node and try to update the distance for the neighbor node. And that may trigger another recursion. Because of this is very simply described and sort of similar to Bellman-Ford algorithm. But because of the characteristics of this aggregate function, we can compile this to Dijkstra's shortest path algorithm if you run it on a single core machine. If you run it on a parallel multi-core machine or distributed cluster, we can compile it to what is called parallel delta stepping algorithm, which is best parallel shortest path algorithm. So the reason why we can apply that kind of compilation optimization is described in this paper in ICDE and VLDB. So if you're interested, please have a look. So now Python integration. So we make it possible to include or embed SociaLite queries inside Python code as long as they are inside this backtick. For this, we extend the Python interpreter to pre-process these SociaLite queries. We support full interoperation between Python and SociaLite, such that from SociaLite queries, you can access Python functions and variables. And also, from Python code, you can access tuples in SociaLite tables. Let me give you an example. So here we have just simple Python code. And then we have this SociaLite query inside this backtick, declare a table, and insert a single tuple into the table. And then we have this Python variable, and we are accessing that Python variable from SociaLite rule. And this $ indicates that this is from Python code. We also make it possible to use Python functions from SociaLite rules. But for functions, we want you to annotate its return type so that we can apply optimization. Finally, you can iterate the tuples in SociaLite table with this kind of for loop. So the point is the Python code is sequentially executed, and the SociaLite rules queries are executed in parallel if you run it on a single machine, or it runs on cluster machines if you're connected to a cluster of machines. So that was all done in Jython. So we extended Jython interpreter. So what about C extension modules, right? We have two options. We can use Jython native interface by this guy Stefan, which is basically to support C Python extensions from Jython to support to make NumPy, SciPy these extensions available in Jython. This project is still in alpha stage, but still already TK-Inter works on Jython. So potentially we can use this JNI to support NumPy, SciPy, these things from SociaLite. Or alternatively, we can also have C Python frontend to make these available from SociaLite. Now some analysis algorithms. We already covered storage path. So this is PageRank algorithm implemented in SociaLite. Actually, parallel and distributed storage path algorithm. The first rule here initialize the PageRank value R for node n at iteration 0. And in this for loop, we are basically refining the PageRank value. I don't have time to describe this, so let's just compare it with the Wikipedia description of the algorithm. The first guy matches to this orange guy here, and this equation is executed at each iteration. And the first constant here matches to the first rule body, where we use 0.85 as the damping factor. And this guy, it matches to this guy here, where we are using the PageRank value of node pj at iteration t to compute the PageRank value of pi at iteration t plus 1, which is basically here. We used PageRank value r of node pj at iteration t to compute PageRank value of pi at iteration t plus 1. And we simply sum all this because we are adding all this. So in this, a couple of lines of SociaLite rule, you have implemented distributed PageRank algorithm. Similarly, for k-means clustering algorithm, which is clustering, given a set of data points, you're clustering into k groups. The way how the algorithm works is that, well, initially you assign the data points to random cluster, and at each iteration, you are updating the center of the cluster, and with that update the center of the cluster by averaging the data point. And then with the updated center of the cluster, you are assigning the data points to the closer center. So that is exactly what we are doing here. So we are updating the center of the cluster by averaging the data point. And here, by using the argument, we are trying to find the the center point that is closest to the current node. So of course, I didn't describe every detail, so you cannot fully understand it, but you can have a sense of it, right? So here we have implemented distributed k-means clustering algorithm in these two SociaLite loops. Similarly for logistic regression, except that we need a few more functions for vector dot operation, vector sum operation, and sigmoid function, which is implemented in either in Python or Java. So let me give you the evaluation number. For first, we evaluate SociaLite single core performance, and then we measured how it scales to multiple cores, and then distributed cluster. So we implemented these 6 graph algorithms, including PageRank and mutual neighbors, which is basically finding the common neighbors between a pair of node. We implemented these algorithms in Java and SociaLite, and we try our best to optimize the Java. And the bottom line is SociaLite is as fast as highly optimized Java, which was about 30% slower than very optimized C++. Okay. Then we see how it scales to 1 to 16 cores for the same algorithm. For these algorithms, it scales almost linearly. With 16 cores, it is about 16 times faster than when you use single core. And for this algorithm, it scales sublinearly. With 16 cores, it's about 10 times faster than single core execution, which is the characteristic of these algorithms. But it shows that for massively parallel algorithm, it scales very well. Then with Intel Research Lab, we compared existing distributed machine learning and graph framework, including combinatorial BLAS, Graph Lab, of course, SociaLite, and Giraffe, which is an open source version of Prigel. These are distributed graph and machine learning framework. And Intel people also implemented native implementation for these algorithms, applying all the possible optimizations. So of course, this is fastest for all of these algorithms from 1 to 64 machines. And for this guy here, counting triangles, SociaLite is almost as fast as the native implementation, which is optimal, very close to optimal. For other algorithms, we are a little bit slower than combinatorial BLA. Here we are a little bit more slower than combinatorial BLA. That is because for these two algorithms, combinatorial BLA has a native implementation, so it's almost like a function call. Whereas in here, we have actually used combinatorial BLA's API to implement this algorithm, so here we are closer. So, notice that all the other frameworks are implemented in C++, or C++, and we are almost the only Java implementation except this very slow guy here. So it shows that the performance of distributed performance of SociaLite is very competitive. Okay. So this is summary, and if you have questions, you can ask me now. You can go to this website to download the binary and have a look at the source code. The source code is in the GitHub repository. You can find it here. And today we are going to have a code review or code walkthrough of SociaLite at 5 p.m. today here at Academia Sinica to some of the students here. And if you are interested, you are welcome to join us and know some of the internals of SociaLite and why it's that fast. So we are going to meet at the first floor of the conference venue at 5 p.m. today. So I guess I have some time to get questions. Okay. So any questions, please?
I have 2 questions. First one is how much time does it take for you to implement this language? The second question is what do you learn the most from this project?
Mm-hmm.
Thank you.
Oops. So for the time, I started around mid of 2011-ish So that gives me about 2.5, 3 years, something like that. And well, I think for the second question, I think I actually, yeah, these are some of the, in terms of engineering effort, these were some of the things that we learned. So the reason why, in terms of distributed performance, the reason why we are fast is that, well, first of all, we use custom memory allocator, which reduces the garbage collection time as well as the memory allocation time. So the one thing with the Java memory allocator is when you allocate an array, not only does it allocate the memory for the array, but it initializes every single entry with default value. We don't need to do that in SociaLite, so we have custom memory allocator. Also, we have very optimized serialization. We do not use Java serialization. This is, in a sense, similar to Hadoop writable interface, but I think we are slightly more better in terms of memory footprint. And we used direct byte buffer for storing data to be sent across machines. So when you use Java direct buffer, Java compiler and Java JVM runtime system tries its best to remove the zero copy so that the network API directly accesses this direct byte buffer. So we remove unnecessary zero copy. And another thing is of course, we have all-to-all connections among the worker node. So they have asynchronous network I/O channels. And for that, for given two worker node, we connect them with multiple network I/O channels. Because if you just use single network I/O channels, if you optimize the entire system component, maybe you can fully utilize its network bandwidth, but it's harder. So with multiple network channels, it was easy for us to fully utilize it. Okay. So, any other questions?
One question.
Hi, thank you for your sharing, and I'm very curious about that. What kind of social network analysis problem has used the SociaLite this package to solve? Because I study social network analysis, and I feel it's very hard to use existed package to do my research. I usually re-implement by a very fundamental package like networks or something.
So for example, Prigel, like that API is very hard to implement.
For example, if I want to do some supervise the page rank, and it's hard to implement from Neo4j or what like this. So I'm very curious about what kind of social network analysis this problem has used this program. Thanks.
So for the benchmark algorithms, we implement, shortest path, page rank, counting number of common neighbors, connected component, counting triangles, clustering coefficient, and we also implement a few other algorithms. For example, betweenness centrality, but that was on a single machine. We also implement Eulerian path, finding Eulerian path, which could be useful for bioinformatics to reconstruct the genome sequence from short read. So they are some of the things that we did. We haven't really applied this to the real data. Well, we did, but just for the experiment. We started discussing with some of the companies, for example, LinkedIn and Line as well, to really apply this. So you're gonna see how it's gonna come out. So but you can, if you're doing research, you can try use it right away. It's in alpha stage, but still, I think for research purpose, it should be enough. So I'm going to wait a little bit so that for those of you who are very busy can go out and take some rest or whatever. But I will give you a demo during the break. So yeah, so I will wait a couple of minutes and then give you a demo, basically using airline routing data. Okay. Okay. Okay, so what I really wanted to do was to use Taiwan public transportation data and apply this kind of analysis, but I couldn't download it somehow. I couldn't find it, so I downloaded airline routing data instead, which is basically connecting, airline connecting from airport 1 to airport B. And I did two very simple analysis. The data itself is small, just a few megabytes, but this is just to give you a sense of the analysis process. Okay, so I ran a shortest path algorithm from Taipei Airport, which gives you how many number of hops away from Taipei Airport for the rest of the airport is. So it gives you for all the airport, it gives you how far away they are by the number of flight changes or by the number of hops. Second one is another very simple analysis. Is I flew from SFO to Taipei directly with EVA airline, and it's 14 hours flight. So I thought it's a little bit too long. So I was thinking maybe it would have been better if I could go somewhere else and take some rest and come back. So I thought maybe it's interesting to find out all the two-hop paths from SFO to Taipei. So that's basically what I'm going to show you here. So we have data here. Well, which is basically, this is, airline name. This is from airport to airport. So this airline flies from this to this airport. And so we have SociaLite interactive shell there. And I'm going to first read the data. So here we have the data on my local machine. So we are going to read the data with this built-in read function, which returns line by line, and then use this split function, splitting it by comma, and only extract the column that we are interested, which is airline from airport to airport. The underlines are simply ignored. Okay, but for we also have another function to read data from HDFS. So you can use HDFS read to read it from HDFS. So I'll copy and paste it in the interactive shell. And then also this guy here. So this is shortest path algorithm. Simply, I ran the shortest path algorithm from. Can you guys read it? I'll make it bigger. So I ran single source shortest path, the same algorithm from Taipei Airport. So I'm going to run it. Oh, thank you. I'm going to run it. Okay, and I will examine the result. But it has too many, results. So I'm going to only print the airport who is far away from Taipei Airport. So these are the airports that are at least, 8 number of hops or number of flight changes away from Taipei Airport. I figured out that these two are heliport, which is simply airport only for helicopters. So no wonder why they are, far away. So this is, I think, a local airport in the United States, and this is a local airport in Canada. So this is just simply shows how the airport that are far away. And for the second analysis, I'm going to run this algorithm, this very simple query here. So from SFO, we take this airline 1 to go to another airport and take airline 2 to come to Taipei. So for that, we just simply joined the route table with itself. Okay. And this shows, let me print out the result. And these are all the different ways to come from San Francisco airport to Taipei airport. For example, you can take American airline to go to Hong Kong, and take EVA airline to come to Taipei. So again, the point is, if you're running a cluster, wherever you are running this interactive shell, for this tuple iteration, in this table, we are going to fetch tuples from the cluster to wherever you're running this this interactive shell, so that you can easily examine the data. So it makes the analysis process a little bit easier for you. Okay, so that's the demo. And again, please, if you're interested, please go to this website and also come to the code walkthrough. Thank you.